Pipelining. Hello learners. If you have to do a time-consuming work and you decide to do it with some of your friends, it will be accomplished in less time. In a similar way, if we want to increase the speed of processor, the concept of parallel processing is used. Pipelining is an integral implementation technique for parallel processing. In this mechanism, the process is decomposed into several sub-processes where each process is executed in a special dedicated segment that operates concurrently with all other segments. Consider a computer system with 5-stage processor organization. This system allows only one instruction to be executed at a time. So this will take 5 clock cycles to complete the execution. Figure 1 depicts these 5 stages, namely fetch, decode, compute, memory, and write. Allowing only one instruction to be executed at a time would lead to consuming a lot of time for executing whole set of instructions. To speed up processing the execution, instructions can be fetched and executed in a pipeline fashion. In pipeline organizations, 5 stages are same. Initially, instruction ij is fetched, and in subsequent clock cycles, it moves through the remaining stages of the cycle. In second cycle, instruction ij plus 1 will be fetched while instruction ij is in the decoding stage. Similarly, in the next instruction cycle, instruction ij plus 2 will be fetched and instruction ij plus 1 will move to decoding stage, and instruction ij will move to next stage of computing where some ALU logic operation is performed, and the cycle will repeat in the same manner. Ideally, this overlapping pattern of execution is possible for all instructions. Figure 2 shows the pipeline method to execute the set of instructions. In the first stage of pipelining, the PC is used to fetch a new instruction. In the subsequent cycles, fetching of other instructions will take place while the previously fetched instructions proceed for their execution. At any given instant of time, each stage of the pipeline is busy in handling a different instruction. While processing an instruction, various information such as register address, immediate data, and the operations to be performed are required at various stages of the pipeline. This information is stored in the inner stage buffers given as 1. Inner stage buffer B1 provides the information of last fetched instruction to the decoder. 2. Inner stage buffer B2 provides the information of source and destination register, immediate value from the instruction, the updated value of PC used as return address for a subroutine call to the compute stage. 3. Interstage buffer B3 carries the result of ALU operation that can be data or an address and is passed to the memory stage. 4. Interstage buffer B4 gives the value to be written into the register file to the write stage. Now moving to the issues related with pipelining. Sometimes a new instruction cannot enter the pipeline in every cycle. This may happen due to various issues known as pipeline hazards. If a pipeline operation cannot be continued without interruption, the pipeline is said to be stalled, and the condition that causes pipeline to stall is called a hazard. In data hazard, value of source operand cannot be gotten when needed. Other causes for hazards are memory delays, branch instructions, and resource limitations. 1. Data dependencies. Data hazard is a situation in which the pipeline is stalled because the data to be operated on is delayed. For instance, consider the following two statements. I1 is to A equal to 3 plus A. I2 is to B equal to 4 times A. Now, if A is equal to 5 and I1 and I2 are executed sequentially, then B should be equal to 32. In a pipeline processor, the execution of I2 can begin before the execution of I1. This will lead to incorrect results as the value used will be original value of A, which is 5. Thus, instructions I1 and I2 depend on each other as the value of A used by I2 depends on results generated by instruction I1. So, to get the same results with pipeline execution to be same as with sequential execution, instructions which depend on each other must be executed in correct order. In cycles from 3 to 5, execution of instruction I1 takes place. So the control signals is set in the interstage buffer B2 for an implicit NOP or no operation instruction that does not modify the memory or the register file. This NOP creates clock cycle of idle time, which is known as the bubble, so that it passes through the compute, memory, and write stages to the end of the pipeline. Handling data dependency. 1. Operand forwarding. Operand forwarding makes use of some special hardware for detecting the delay, and then delay can be avoided by routing the data through special paths between pipeline segments. For instance, instead of transferring an ALU result into a destination register, the hardware will check the destination operand, and if it is needed as a source in the next instruction, it passes the result directly into the ALU input and thus bypasses the register file. Implementation of this technique requires some additional hardware pass through multiplexers as well as the circuit that detects the conflict. Value from ALU is directly sent from the temporary register to the multiplexer for further calculation rather than storing it in some register. 2. Handling data dependencies in software. Instead of using hardware approach, an alternative approach can be employed to leave the task of detecting data dependencies and dealing with them to the compilers. Whenever a compiler identifies a data dependency between two successive instructions, ij and ij plus 1, it can deal with it by inserting nope or no operation between them. The nopes allow the necessary delay required for the new instruction to read the value from the register. Introducing nope instruction simplifies the hardware implementation of the pipeline, although the code size increases and execution time is more than the operand forwarding approach. The compiler can optimize the code to improve the performance and code size by moving useful instructions into NOPS slots. To let instruction I1 complete its execution, NOP is inserted between instruction I1 and instruction I2. 2. Memory delays. Pipeline stalls can also be caused by the delays arising from the memory. For instance, load instruction may not be able to get its operand from memory in one clock cycle for the data requested. The data requested may not present in the cache known as cache miss that results in delaying the subsequent instructions. When there is a data dependency involving in load instruction, then an additional type of store which is related to memory occurs. This can be understood by considering the following instructions. Load R2, R3, subtract R9, R2, 30. Assume that the data for the load instruction is found in the cache and requires only one cycle to access the operand. In subtraction operation, R2 is an operand, but in load instruction, R2 is a destination address. In this case, operator forwarding cannot be done because the data which is read from memory, in this case cache memory, is not available until it is loaded into the register RY at the beginning of cycle 5. Consider figure 6, which shows the data path of processor. This causes the stalling of subtraction operation for one cycle to delay the ALU operation. One cycle stop caused by this type of data dependency can be avoided by the compiler. For this, instructions can be rearranged to insert a useful instruction between load instruction and the instruction that is dependent on the data read. The inserted instruction avoids the bubble that otherwise would have been created. The hardware induces one cycle store implicitly if compiler fails to find a useful instruction. If the hardware does not deal with it, then the compiler inserts an explicit nope instruction. 3. Branch delays. In an ideal pipeline execution, a new instruction is fetched every cycle while the previous instruction is still being decoded. Branch instructions are used to direct the program to a new sequence of execution, but it is necessary to determine whether and where it has been branched. Branch instructions may incur branch penalty, reducing the performance as expected from the pipelining. Unconditional branch instruction ij is a branch instruction followed by instruction ij plus 1 and ij plus 2 with the target of branch at ik. Now the branch instruction is fed in cycle 1 and decoded in cycle 2, and the target address is computed in cycle 3. But meanwhile, in cycle 2 and 3, instructions ij plus 1 and ij plus 2 are fed respectively. But in cycle 4, instruction ik is fed since branching address was computed in cycle 3. So, as a result, instruction ij plus 1 and ij plus 2, which were fed, has to be discarded. The resulting two cycles delay constitutes a branch delay. Branch instruction represents 20% of the dynamic instruction count of most programs. Dynamic instruction count takes into consideration that some instructions are executed repeatedly. To reduce the branch penalty, it is necessary to compute the branch target address earlier. It is possible to determine, compute, and update the program counter in the decode stage rather waiting for the compute stage. This would help to reduce branch delay. Instead of fetching instructions ij plus 1 and ij plus 2 incorrectly, only one is fetched incorrectly. For this, it is required to modify the hardware shown in figure 9. The other in the figure needs to modify the address in PC with increment of 1 in every cycle. A second adder is required in the code stage for computing the target branch instruction for every instruction. Now, when the decoder determines that it is a branch instruction, then the computed target address will be available before the end of the cycle. II. Conditional branching. Conditional branching involves instructions which transfer control to some sequence of instructions when some condition is fulfilled. For instance, consider the following instruction: branch if R5 is equal to R6 loop. The result of the comparison determines if the branch is taken. So to reduce the branch penalty, the branch condition needs to be tested as early as possible. As we computed the target address in the decode stage for unconditional branching, the comparator that tests the branch condition can also be moved to the decode stage. This enables the conditional branch decision to be made at the same time that the target address is being decoded. 3. Resource limitations. Pipelining enables overlapped execution of instructions, but whenever there are insufficient hardware resources to permit all actions to proceed concurrently, then the pipeline stalls. For example, if two instructions require accessing the same resource at the same time, then one of them has to be stalled to let the other use the resource. Using separate caches for instructions and data allows the fetch and memory stages to proceed simultaneously without stalling. That brings us to the end of this section. Thank you.